Assalamu alaikum. So let's get started. It seems we don't have much time today because there is also going to be a quiz at the end of the class. So I would like to this is exciting news, right? Alright, so let's get started, please. And another small announcement is that I'm also posting a homework today, and that homework is going to be due next Friday at 10 a.m. Alright? So that is also going to be a collaborative homework. Alright, so I think it's time to start now. You at Red Sea. अच्छा, अभी तक हम ये देख चुके हैं कि जो मैटर है उसकी एक पार्टिकुलेट एग्जिस्टेंस है. So, do you know of, can you tell me of a phenomenon or remind me of a phenomenon or an effect that shows that matter has particulate existence? Ji? Sorry? Faraday? Bolo? Electrolysis? Faraday's electrolysis, yes, is one phenomenon. The Bohr's model is in fact based on a particle called an electron revolving around the nucleus. Rutherford's model is alpha particles that are bombarding an atom and they are being deflected by the strong repulsive force from a positively charged particle which is called the nucleus. So all of these shed light on the particulate nature of matter. And we've also seen that radiation has wave-like existence. Can you remind me of a phenomenon that reveals the wave-like nature of radiation? The double slit experiment. Have you ever observed anything in your lives? Yes, yesterday we looked at diffraction patterns from a single slit and from a double slit, as well as from a reflection grating. So these phenomena shed light on the fact that radiation, such as light, must be made up of particles. Now what we are going to do now is we're going to look at the particle nature of radiation. And this is where most of quantum mechanics started. So quantum mechanics took its root when the particulate nature of radiation was being developed. In fact, we've already seen the fact that radiation comprises photons, and each photon is a particle. So many times I've drawn the photon by a sphere, and this particle carries an energy hf or h bar omega, and it carries a momentum which is h over lambda or h f over c. So this, when I write all of this down on the blackboard, this actually means that the photon, which is a particle of radiation, which is a quantum of radiation, which is a packet of energy, has a certain momentum. It can transfer its momentum to another particle. For example, if I have my hand here and photons are striking this hand, and if these photons have a high enough momentum, which means they are of very short wavelength or they are of very high frequency, they can impart momentum to the hand, and my hand can tilt. In fact, it can gain some of the momentum. So photons carry momentum, but another question that comes to our mind is that if photons have momentum, we are associating a wavelength with the photons, we are associating a frequency with the photons, f, omega, lambda, but these are wave-like properties. So what really is radiation? So this is something that we're going to explore next week when we study wave-particle duality. But for the time being, what I would like to focus is whether radiation can act like particles, and what were the first original experiments that were performed in the beginning of the 20th century and the late 19th century, which actually showed that radiation is comprised of photons, quantized particles. So there were two basic experiments. One was an understanding of black body radiation. And this understanding of black body radiation was done in 1900 by Planck, Max Planck. And 1900 is considered to be the year of the discovery of quantum mechanics. This was the first idea that could be hailed as the curtain raiser of quantum mechanics. But the idea is slightly complicated. Let me give you a brief overview of the idea, and I will not go into many details. If this were a sophomore class, perhaps I would have discussed it, or a junior level class, but not at the level of freshmen. So black body radiation, we've already seen in disguise. We have a solid which is hollow from the inside, and the walls of this solid are made of a certain material. This solid is kept at a temperature capital T. Now the harmonic oscillators inside the solid have quantized levels. So you can draw a harmonic oscillator representing the atoms. The energy levels are quantized. And what's the energy spacing between any two levels? It's h bar omega. And then we also have the Boltzmann distribution. So the population in a certain level E is proportional to exponent minus E kBt. So at a particular temperature, these levels will be occupied with certain probabilities. And so on. So the populations decrease exponentially because the energy is going up. And this energy in fact is simply n plus half h bar omega for a harmonic oscillator. So when transitions take place between these energy levels, there is a constant process of equilibrium, dynamic equilibrium. Even though the populations remain constant with time, if this system is in equilibrium, but it's very possible that a transition from an upper level to a higher level takes place, emitting a photon, a transition from this level to this level takes place, emitting a photon, and then these photons are constantly being absorbed as well, such that the absorption and the emission, they match out in such a way that this population distribution is maintained. So if you leave this object for a certain amount of time, you will have photons collecting inside the cavity, right? And those photons will have certain frequencies. They will have frequencies omega, 2 omega, 3 omega, 4 omega, 5 omega, and so on, corresponding to the spacing between these energy levels. So with time there will be a gas of photons. And this radiation is called black body radiation or cavity radiation. And by looking at the spectrum of this radiation, Planck was able to tell that the atoms inside the walls of the cavity, they have quantized energy levels. And their populations are distributed according to the Boltzmann factor, which came about in the early 1800s. So this was one of the first ideas that gave birth to quantum mechanics. But I will not go into too many details because it's a bit more sophisticated argument, but here's a semblance of the idea, and I hope you understand what I've said so far. The other major experiment which led to the consolidation of the idea of quantum mechanics was the photoelectric effect. So the black body radiation in fact told us that radiation comprises particles, and these particles have quantized energies, and they were called quanta by Planck. So this was one of the first ideas. The second idea was the photoelectric effect. Excuse me, you're in a classroom. I'm speaking in front of you, so you have to listen to me, please. Have you ever heard the name Hertz? Hertz. So Hertz, around the 1880s, discovered that if you have a metal and you shine light on it, electrons are ejected from the metal. So this is called the photoelectric effect. Then in 1902, Philip performed an experiment. The basic idea of the experiment was follows. You must have already seen this. You have a glass tube in which there is a metal which is shaped in a concave form. You have a very sensitive galvanometer or an ammeter, and you are able to apply a variable voltage. This is a potential divider kind of arrangement. Okay, and you are also able to measure the voltage. ठीक है, ये उसका एक्सपेरिमेंटल अरेंजमेंट था. अब ये एक इवैक्यूएटेड ग्लास बल्ब है. और इसके अंदर ये दो इलेक्ट्रोड्स हैं. So what happens is that excuse me, a source of light, a lamp, is placed at a certain distance, and in the path of the light there is a filter that can select a certain wavelength of light. Light comes in, falls on this electrode, this cup shaped electrode, One adjusts the voltage V and measures the current. Alright, so this was the experimental arrangement of Philip. Now what Philip observed was something very interesting, but he did not have an idea of how to explain his experimental results. Now what did Philip observe? No matter how hard you try and how hard you study in these 20-30 minutes, you'll not be able to do the quiz if you haven't studied already. Now it was well known that when light falls onto this metal, electrons are ejected from the surface of the metal, and if there is a positive potential on this plate, these electrons will be attracted towards the anode. They will be attracted towards this electrode and they will form a current. So, however, if this electrode were made negative, that is, the direction of this battery is reversed, then electrons will find it difficult to reach this electrode and the current will finally diminish. But even if this electrode were negative, there would be some current because the electrons are coming with some energy. I have a negative potential there and I am a negatively charged particle. I am being repelled by that wall, right, because that's negatively charged. But if I have enough kinetic energy, I'm able to surmount the Coulomb barrier and steadily move towards the wall. If I have more kinetic energy, I have a higher likelihood that I'll be able to overcome the potential and reach the wall. So if that wall is made very negative, only the most energetic electrons can reach the electrode. And at a certain point, if that wall is made negative enough that no electron can reach the wall, the current will go down to zero. Alright? So my measurement of the stopping potential, how large a negative voltage do I require on that electrode, is a measure of the maximum kinetic energy of the electrons. So what Philip observed is that if he plotted the maximum kinetic energy of the electrons on this axis and the photocurrent small I, which was measured by the galvanometer, he obtained a graph like this. So this was for a certain intensity of light I1. Now don't confuse this capital I with this I. This is the photocurrent and this is the intensity of light. The intensity of light means how bright is this source. The intensity can be changed by, for example, bringing the lamp closer or further away from the glass tube. If it's further away, the intensity drops as 1 over r square, 1 over the distance of the lamp from the bulb. So the intensity can be changed by moving this lamp close to the tube or further away. So that will be the brightness of something that is far away. The intensity of its light reaching us will be smaller, even though it may be more intense. Most of the stars that we see on the night sky, they have a higher brilliance than the sun, but they look dimmer, much dimmer, because they are further away. So you move this lamp further away, the intensity of light that is reaching this electrode is continuously decreasing. So for a particular intensity of light, this is the curve that Philip obtained, and this actually baffled him. It confused him because why was he confused? Let me tell you why. He increased the intensity. And obtained another curve. So this I2 is higher than I1. And both of these curves met at the same point. Let's call this axis, instead of K max, let's call this axis V naught E, where V naught is this potential, the potential that is applied here. You increase the potential, make it more positive, the photocurrent does not change, it remains constant for a given intensity of light. However, for a higher intensity, the same voltage will lead to a higher photocurrent. This is fine. Higher the intensity, higher the photocurrent. This is explained classically. However, the problem is that both of these curves intersect at the same point. So this value of energy is minus the stopping voltage times E. The stopping voltage is now negative. So this is some negative voltage that is being applied. So the same stopping voltage will diminish the currents for different intensities to zero. This we know is a measure of the maximum kinetic energy. This is the maximum kinetic energy of the electrons. It has to be proportional to the maximum kinetic energy of the electrons. Somehow. Now what does all of this mean? You have a certain intensity of light and then you increase the intensity of light. What do you expect classically? You expect that higher the intensity of the incoming light, the more the energetic electrons would be released. So higher the intensity, the ejected electrons must have a higher energy. So what you classically expect is that if I2 is higher, this curve should actually go like this. Which means the maximum kinetic energy should be higher. A more negative voltage should be required to halt the electrons. But this is not something that is actually observed. It's the same stopping voltage for both the intensities, which means that the maximum kinetic energy has nothing to do with the intensities. What we classically think is that if you have a more intense wave, it will bring in more energy. A higher intensity will bring in more energy. Classically, the formula goes like this. Intensity I is energy per unit time. Of course, area as well. E T A. So the energy that is brought in is equal to I A T. Higher the intensity, higher the energy. So this is a classical result. This is what Maxwell had in his mind. Higher the intensity, higher the energy. Now you're increasing the intensity here. So the intensity of this light that is reaching the electrode is higher, which means more energy is falling onto the electron inside this metal. So when they are ejected, they must have a higher energy, and the maximum kinetic energy of the electrons ejected should also be higher. So a higher stopping voltage is required to stop the electrons. But what is observed is that it's the same stopping voltage that is required to stop the electrons. The other observation was the following. If you have changed the frequency of the incoming light by adjusting the filter, so you can have filters for different frequencies, and you have the photocurrent, first of all, the observation was, alright, Oh, so suppose here you have the stopping voltage Vs. The observation was that the stopping voltage is in fact dependent on the frequency. So you keep I constant, and what you observe is a graph like this, which means I is constant, the intensity of the incident light is constant, but you're increasing the frequency of the light, you're changing the color of light, and the stopping voltage is constantly on the rise, which means that the maximum kinetic energy of the electrons is on the rise, but you kept the intensity constant, which means that classically you kept the energy that is incident on the electrode constant. The stopping potential should not change. But here what Philip Leonard observed is that even if you kept the intensity constant, you keep on increasing the frequency, the stopping voltage keeps on increasing, which must mean that the kinetic energy of the electrons is increasing with frequency and not with intensity. And there is a certain threshold, F naught. Where the stopping voltage is 0, which means the voltage that is required to stop the electrons is 0. This means that no electrons will be ejected if the frequency is less than F naught. So this is something that actually baffled all physicists of the time, and there is no classical explanation. Another classical problem was that, you see, this energy is dependent on the time. So you have a metal piece, say sodium metal, and you're shining light onto it. You turn on a bulb and you shine light on it, and now it heats up, it starts heating up, the temperature increases slowly. This is how the process of energy transfer takes place. Now every metal has a certain work function, phi. A certain minimum energy is required for the electron to be ejected from the metal. That is called the work function. So suppose the work function is 3 electron volts. The energy supplied by these waves must be at least 3 electron volts, so that the electrons can be ejected. But the energy is proportional to the time. When the bulb is switched on, the thermal energy has not increased by 3 electron volts. It slowly builds up. It should slowly build up if you were to believe classical mechanics. And it should actually take a very long time for the electrons to be ejected. Suppose 1 day, a month, or a year for the electrons to be ejected. There's a very nice example in Survey's book. So this should actually be a very slow process. So you keep on shining light onto it and wait for a very long period of time. The thermal energy goes up, and when enough energy has accumulated inside this material such that the work function is surpassed, that is, the energy that has been accumulated is greater than the work function, would the ejection of electrons initiate. So it would take actually very long for the photoelectric effect to take place. But that's not observed. The photoelectric effect is instantaneous. It happens of the order of nanoseconds. So the classical result has failed us. So we must have a quantum explanation of what is actually happening. And that quantum explanation I'll start off on Tuesday. But it was the genius of Einstein in 1905 that he presented an explanation of the photoelectric effect. 1905 में उसने 3 पेपर लिखे थे आइंस्टाइन ने, एक ब्राउनियन मोशन पर, एक स्पेशल रिलेटिविटी पर और एक फोटोइलेक्ट्रिक इफेक्ट पर. और तीनों पेपर ऐसे थे लॉजिकल क्लियर पेपर्स कि तीनों पे उसको नोबेल प्राइज मिल सकता था. लेकिन 1921 में जब उसको नोबेल प्राइज मिला तो सिर्फ फोटो इलेक्ट्रिक इफेक्ट की वजह से मिला, और उसमें रिलेटिविटी का जिक्र भी नहीं था। तो ये आइंस्टाइन का जीनियस था कि उसने सिंपल आर्ग्यूमेंट्स इस्तेमाल करते हुए इन एक्सपेरिमेंटल रिजल्ट्स को डिस्क्राइब किया। और एक बात आप दोबारा ये ज़हन नशीन कर लें, देख लें कि एक्सपेरिमेंट्स परफॉर्म हो रहे हैं। क्वांटम मैकेनिक्स की बर्थ एक्सपेरिमेंट्स का शाखसाना है। एक्सपेरिमेंट्स परफॉर्म हुए, उनके नताइज समझ से बाला थे, समझ में नहीं आ रहे थे, तो उसके बाद थ्योरेटिशियंस ने उन एक्सपेरिमेंटल रिजल्ट्स को एक्सप्लेन करने के लिए क्वांटम मैकेनिक्स के आइडियाज की दाव बेल डाली। सो वेलकम एवरीवन टू द अरीना ऑफ द क्विज। Thanks for being in time for the quiz. Thank you very much. So please be seated. We're going to distribute the quizzes. It's going to be about a 25-minute quiz. Only one question.